Hello everyone, in this part we're going to go over section 13.d, and this is related to the secant function. So in this scenario we have two buildings, and we have two people that lives in these apartments, are Ronnie and Sam, and they live in buildings across the street from each other. The buildings are going to be 150 feet apart. And when Ronnie looks out of his windows to Sam's, he measured that he has a 45 degrees angle between his line of sight and the horizontal that will give with Sam's building. We want to know how far is Ronnie's windows from Sam's window. And if we think that the apartment are close enough for them to be able to share a wireless internet connection. So by the setup here, you notice that we can create triangle. We can create a right triangle here where Ronnie is looking up an angle of 45 degrees, and we want to measure this distance d, because that will allow us to know if the routers are going to be good enough to provide both apartments with internet service. Now, just from this setup, we have that the cosine of 45 degrees, which is pretty much the adjacent, which is 150 feet over the hypotenuse, which is d, will create a relationship between the quantity and the trigonometric angle. However, we can't find out what d is actually in this case, with d being 150 cosine of 45. And by the definition of secant, since the secant function is 1 over cosine, this can be seen as 100 in secant of 45. This result is going to give me around 212 feet. And so the distance is probably going to be too far for the wireless router unless they have a really powerful antenna. Now, on general definition, if we're just thinking about a given angle, just to check if another apartment will work, we decide that we're looking at a different angle. Instead of just 45, we're going to create this as an angle theta. And so this is going to give us a similar relationship. We're going to have that the cosine of theta is going to be 150 over d. And that's going to imply that d is just 150 over cosine of theta, or 150 secant of theta. Okay. We could be able to just find out what are going to be the possible angles that are going to give me a distance that might work for getting a router in range. Now, because cosine of theta has zeros at pi half and minus pi half, like we discussed before in class, then we can assume that the inputs are as well between minus pi half and pi half. That also makes sense because if they are at certain angles like pi half or minus pi half, that will mean that they're living pretty much in the same building. Now, if we use a calculator just to find out how this will look like, let me show you a bit of that. Then this will be what happens. So this is the graph of secant, and so the range for this will cover enough so that we have a range of 200 feet. This is going to be between minus 0.72 radians and 0.72 radians. These are the angles that will either locate a window across the street within range of Ronnie's router or in the same building. In the same thing, we want to know what is the minimum value of the distance and what is theta corresponding to. While interpreting, of course, these values in the context of the problem. Now, the minimum value, which is d of 0 for this case, will be 150, since it's 150 over cosine of theta is d of theta, then d of 0 will be just 150. This value is going to indicate that the closest window is 100 feet away, which is, of course, across the street at the same level. Now, when we're getting closer to values like pi half, and this in the context of, again, or a scenario, means that run is looking straight up. So this means that the corresponding window is very, very far away. So in this scenario, that will not work for having a shared connection of internet. Now, this is for the definition of secant, and that helps us explore a little bit secant. But where we really want to pay attention is how to use identities now involving secant and tangent, which is part of 13E. So the first thing is that you gotta recall that when you have right triangle, then you can have the trigonometric identity that is coming also from the circle, which is the sine square plus the cosine square equals 1. Now, notice that if we divide both sides of this equation by cosine square, things are going to happen. So notice sine divided cosine square plus cosine square divided cosine square equals to 1 over cosine square. Okay, we're dividing these main identities by cosine square. Sine over cosine we know is tangent, so this can be defined as tangent square of x. Cosine square of x over cosine square of x becomes 1, and 1 over cosine becomes secant. So this will be secant square. So notice that we have a new identity. This new identity is tangent square plus 1 equals to secant square. Now, given that, we could, in a triangle that is with a side of length 1, define the rest of the sides. So for example, we're going for opposite. The opposite over the adjacent, which is 1, will be the tangent of x. So this means that in this triangle, this will be the tangent of x. And now the hypotenuse, if we have adjacent over hypotenuse, that will be the cosine, right? But notice that the adjacent is 1, so this can be seen as 1 over cosine of x equals the hypotenuse, and this is secant. So if we have a triangle like the one we have here where the adjacent side measures 1, then we're going to have that the hypotenuse measure is going to be secant of x, and the opposite measure is going to be just the tangent of x. Now, notice that with this same setup, if you apply the identity of hypotenuse square equals the square of the sides, you're going to get that secant square is 1 square plus tangent square. So this is validating the identity that we just got here, coming from this main identity. So now, why is this type of identity useful? So we just defined the function tangent and the function secant, and now we're finding relationships to interchange secants with tangent. Now, this is going to be especially useful when we're trying to make conversions of things where we don't have immediately one of the values or the other, so where we cannot get the tangent because we either don't have, let's say, the opposite value. Remember, secant is just in terms of the adjacent because it's related to the cosine. So if I don't have the opposite, I can transform a tangent into a secant, and that can reduce the amount of values that is needed for solving anything. Now, in this equation here, part C, we have the biologies in question 1, in the particular context of this 13E identity. We have that a biologist is collecting data on the behavior of birds perching in trees, and she would like to measure the distance d from an observer on the ground to a bird in a tree, and also the height h of the bird above the ground. And so we can kind of relate this to quantities by using what we have here. Notice that what that gives is a triangle. It's a right triangle. Although my picture is not looking like a right triangle, let's assume this is a right triangle. And that's going to have a 42 degrees angle. And this is the measure D. And we have that the distance from the base of the tree to the observer, that is here. Observer, this is the tree, and this is the bird. So from the observer to the tree, there's 22 meters. And so that means, according to this, that this value here will be 22 tangent of 42. When it was 1, I can just relate this with tangent. When it's not 1, then I can just say, well, this is 22 tangent of 42. Okay, and so this means that I can also interpret the distance here as 22 secant of 42. And that's the help that this is going to providing here. Now, this result gives me that the bird is around 19.8 meters above the ground. Sorry, not degrees. Yeah, this is the value for the tangent, sorry. So this is 19.8. Okay. The distance that is measured by the diagonal, which is the distance from the observer to the bird, now that one will be 29.6. And so this is some of the uses of how the tangent and secant equations can come into the right triangle. However, they're not as natural as sine and cosine. So if you prefer to use sine and cosine because you know them better, that's still a good approach. You can still do this instead of 22 secant. You could do perfectly 22 over cosine, and that will be no issue. Now, some of the applications of knowing the transformations between tangent and secants is going to help in things like solving equations and trigonometric identities. One example of this will be this following function here, 1 plus tangent square over 1 minus tangent square. We want to use the identity that we got first to transform this into terms of the secant function. And so remember that every time that we're making transformation, we aim to start from one side, and we gotta describe carefully where are we going to reach on the other side. So in this case, tangent square, and just recall from here, can be seen as secant square minus 1. So this can be seen here as secant square minus 1. Or 1 plus tangent square is also secant square. In any of the two cases, this will work out fine. Here, secant square minus 1 as well. Notice that 1 goes away with the minus 1, and this is becoming secant square. And now this minus with minus here, it becomes a plus. and we have 2 over secant squared. So the transformation of this function in terms of secant becomes secant squared over 2 minus secant squared. Now, this can be used to simplify things when we assume that we're using secant as 1 over cosine. So if we use now the fact that secant is 1 over cosine in here, notice that this secant becomes 1 over cosine square. In here we can transform this in 1 over cosine square as well. Now we multiply cosine square up and down on both sides, and notice that if I do multiply cosine square up, this is going to cancel this out, and this is going to transform into 1. And if I multiply by cosine square down, this becomes 2 cosine square of x, and then this becomes a minus 1. So 2 cosine square of x minus 1. But that identity sounds familiar. That identity sounds like cosine of 2x, right? That's one of the double angles identities. And so this is 1 over cosine of 2x, and then if 1 over cosine is secant, then we can see this as secant of 2x. Oh, so we just found an identity for the secant of 2x. We just found that secant of 2x is equals to 1 plus tangent square over 1 minus tangent square of x. Okay, so in the last part it says Sarah is looking for an angle sum to help her compute secant of x plus y. So notice that this is something that we can get from here, probably from just a similar process that we got to do here. But if we're doing secant of x plus y in M5, notice that this is just going to be 1 over cosine of x plus y. And then all this is going to depend of the formulas that we already have for cosine. So this is one of the advantages of already being very careful in the introduction of cosine and sine, because all the other trigonometric functions, whether it's tangent, secant, cosecant, or cotangent, they're dependent in just sine and cosine, and I can just write everything else in terms of them. So as you can see, cosine of x plus y becomes cosine of x, cosine of y, minus sine of x, sine of y. And that pretty much is the end of 13E. So again, remember, for anything of these things that you're doing on your own, just try to complete this lesson on your own and get to the most that you can. This will be here as a solution, but it's very useful to me to understand where are you struggling. So just don't copy solutions, just make sure that you do what you can on each of these lessons.